Good afternoon, everyone. My name is Omar Ayubi. I'm here with.
I'm Chanatan.
And I'm Alland Magyawi, and this is Project S.P.A.W.C.
Project S.P.A.W.C. is a solar-powered atmospheric water collector. Our advisor is Dr. Robert Boehm. And let's get started here. Our project is based on the fact that the atmosphere contains millions of gallons of water. And this is not in the form of a liquid. This is in the form of vapor. And this can be felt in humid areas where there's a high saturation of water in the air. You can harness in areas such as subtropical areas in the near the equator, and such as Florida. And harnessing this would be important as our project basis, because you can eventually, in areas where they don't have access to water, clean water, this is essentially clean water. Past contributions include the Nappen's air well, which is here. Giant dome built in 1931. At the center, there's pipes. At night, cool air works its way through, cools down the pipes, and the walls are very thick. So throughout the day, the pipes are kept cool. And as hot air comes in contact with the pipes, water is accumulated and then drips down and people can go in and drink. This device right here created about 5 gallons a day, which being 45 feet tall, it was very efficient. So throughout the years, there have been many more designs and the same concept. Recently came out the water mill, which costs $1,200. It does the same exact thing. Sucks in air and then outputs water, drinkable water, generally about 3 to 5 gallons a day. And that, again, is very expensive. And we hope to achieve this by making it cheaper.
I'm here to discuss our customers and our profitability. Our product is designed to reach people who wouldn't be near a traditional water source, like, say, example, your rivers, oceans, running water in general. Example of this is the Red Cross at a disaster relief site. Say, rather than having to bring their truck from a distant water source and bring water to the people, they'd be able to set our product in multiple locations and provide a constant flow of water for the people. Other examples would be single-family homes in third world countries, military bases, and basically anybody else who needs water. Feasibility, we believe our product is very feasible because we're using basic knowledge from heat transfer, thermodynamics, as well as controls. And the technology has already been proven, such as with Nappen's air well, as far as the, excuse me, and with the air mill, or water mill. What sets our product apart is we'll be using solar technology, so it'll be much greener and more affordable. Chan?
So our objectives for this product include, again, we're going to make it solar powered, roughly generate about 1 kilowatt hour with battery storage. So that it can be utilized at night. And then we're aiming for generating about 3 to 5 gallons a day of clean water production, and cost less than $500, as low as we can keep it. And our goal is to bring clean water to where it's not readily available.
Okay. The theory behind this device is based on the concept of humidity and dew point. Relative humidity is basically a ratio between the amount of vapor that's in the air over the maximum amount of vapor that the air can hold. So basically, if the air had a high humidity, it also means it's easier for the vapor to condense into water. And the way we choose to do that is by cooling down the air temperature to its dew point. Now the dew point is the temperature which the air has to be cool to in order for the vapor to condense. And the picture right here is the example of the dew point. When the water hit the surface that's cooler than its dew point, the droplet will be formed. And the produced water, it can't really be used right away because the air has many things that we don't know of in it. So it has to be filtered before use. This is schematic.
So here's our thermodynamic schematic of our design. So it's basically two phases. Comes in two phases. On the right, you see the is just humid air coming in and being filtered. There might be particles in the air that's not clean. And then as soon as the humid air comes in contact with the cool surface, it condenses and gravity just takes hold and brings it down, and it drops into a tank, accumulating clean water, and then it's pumped, and again it goes through another filter and therefore becomes drinkable. The phase to the right is the refrigeration cycle. Basically, the refrigerant is compressed by the compressor and is condensed, and by the heat sink goes through the expansion valve, and that way is keeping that coil, the cooling coils, it keeps the temperature right below the dew point, and that's how we're able to generate the water, extract the water from the air, and that's our basic schematic. Go ahead. Add in. That's it. Yeah.
And here's a timeline for this semester. This week we finished the conceptual design. In the week 8, we do the thermal and heat transfer analysis. Week 9, we working on the CAD. Week 11, we do stress strain analysis. Week 13, we look at the material and things that we need. Week 14, we start working on the final report, and week 15, we submit it. That's it.